Let me give some results that will help us orient some of our linear algebra and calculus tools toward what we need to develop least squares, kind of thinking about these tools in a little bit more of a statistical sense. So take, for example, some matrix derivatives that come up very commonly in statistics. Imagine if I have a function f and it's from Rp to R, where f is a linear function. So f of beta is A transpose times beta. And in this case, I'm going to assume that A lies in Rp. Then the gradient of f is simply A. We write it as the transpose of what was in the argument of f, simply because we want the gradient to be a p by 1 vector. Now imagine if A is a matrix, a p by p matrix, and now f is no longer a linear function, but a bilinear function, specifically a quadratic form, b transpose a beta transpose a beta. Then the gradient of f works out to be 2a transpose beta. We'll use those matrix algebra results when we derive least squares. Let's just go through an example of using these results. Imagine if my f of beta was the function y minus x beta transpose times y minus x beta. If I expand that inner product out, I get y transpose y minus 2y transpose x beta plus beta transpose x beta. So if I take my gradient with respect to beta in this case, this term drops out. This term is linear in beta, and so we transpose that and we get x transpose y, negative 2x transpose y. And this term is a quadratic form in beta, so it works out to be 2x transpose x beta. Let me give another couple of useful matrix algebra results for the next couple of lectures. Throughout, I'm going to be assuming that y is a vector in Rn, x is a matrix of size n by p, where p is less than n, and in this case I'm going to assume x is full rank. Jn means a vector of ones of length n, whereas Jn by k means a matrix of ones of dimension n by k. One thing I'd like to note is that 1 over m y transpose Jn is simply y bar. I would also note that 1 over n can be written as Jn transpose Jn inverse, simply because Jn transpose Jn is the sum of a bunch of 1's squared, which is 1. There's n of them, so the inverse of that is 1 over n. So we can think of y bar as 1 over n, Jn transpose Jn inverse, times Jn transpose y. Furthermore, if we wanted to mean center our vector y, we would get the vector y tilde, and we could write that as y minus Jn times y bar. I would note that y tilde is exactly y minus Jn y bar times, which is equal to, I can plug in for y bar here from what I have right here, and I wind up with y minus Jn transpose Jn inverse, Jn transpose times y. I can then factor this y out to get I minus Jn transpose Jn inverse, Jn transpose times y. What we'll find is that matrices like this, I minus this form, matrix times matrix transpose matrix inverse matrix transpose, will exactly remove the linear effect of that matrix from the vector y. In this case, we want to remove the effect of any constant from y. We'll see that. We'll develop that very much so over the next couple of lectures. Note, we can very easily show that y has mean 0. The centered y tilde has mean 0, since if we were to multiply it times Jn, we get Jn transpose times this vector times y. The multiplication of these two is just Jn. The multiplication of these two is Jn transpose times Jn, then times that inverse, which will be I, which leaves me with Jn transpose. So this works out to be Jn transpose times Jn times y, which equals 0. Notice we can do the same thing to the matrix X. If we pre-multiply X by this matrix, then it works out to be what I would label as X tilde, a matrix with the mean-centered columns of X. I think probably the easiest way to show this is simply to write X out as its columns, its P columns, and that, remember, the matrix multiplication would simply multiply this guy by each column. And as it does that, just like it did it for the Y, it's going to mean center each of those columns. I would also note, and you can check this by yourself, that the matrix I minus Jn, Jn transpose, Jn inverse, Jn transpose, that is exactly symmetric and idempotent. And this matrix right here is also symmetric and idempotent. And this matrix here, I, of course, is also symmetric and idempotent. If I consider these centered versions of the data, consider y tilde, the centered y's, and if I take y tilde transpose y, that's exactly the sum of yi minus y bar squared. I would also note that I can write y tilde transpose yi as y transpose times this matrix, which I do not need to include a transpose because it is symmetric, times itself again, times y. Since this matrix is idempotent, I can write that as it's just one version of it to see that this sum right here, the sum of the squared deviations of the observations around their mean, is a fairly simple looking bilinear product or quadratic form with this as the interior matrix. So if we were to pre-multiply by 1 over n minus 1, we see that the sample variance is y tilde transpose y tilde, or this matrix then again times 1 over n minus 1 out front. We can do the same thing with the X matrix. Instead of multiplying a quadratic form with a vector, imagine if I were to pre-multiply by X transpose, and post-multiply X by this centering matrix right here, and then multiply by 1 over n minus 1. That winds up being the sample variance covariance matrix of the data matrix X. Let's see this. So if I write X as the partition matrix of its columns, x1 to xp, then X transpose is again the partition matrix of its columns transposed now as rows. Here I've written this out. So this equation right here with the asterisk, here it is again, is 1 over n minus 1 times X transpose times this matrix times X. If I simply carry out the rules of multiplying through partition matrices, I wind up with x1 tilde transpose x1, x1 tilde transpose x2, x1 tilde transpose up to x1 tilde transpose xp, and so on. And that is simply all of the centered columns of X taken as an inner product with the associated other column of X. And that is nothing other, when I multiply all these elements by 1 over n minus 1, all of the variance terms down the diagonal and all the relevant covariance terms in the off diagonal. So when you see this matrix right here is nothing other than 1 over n minus 1 x tilde transpose x tilde. So whenever you see an x transpose x or an x tilde transpose x tilde, think of it statistically as it's getting at something that's a lot like a variance-covariance matrix. It's exactly a variance-covariance matrix if we centered the columns in this way.